Okay, so today we're going to follow those rules on electronic configurations, and then we're going to see where there's exceptions to those rules. Okay? And the reason why we're studying the exceptions is not because I expect you to memorize a whole bunch of stuff, because there's exceptions all over the table. But I want you to understand the reason for the exception, because the reason for this exception is one of the reasons we need to talk a lot about next chapter. Okay? So the underlying reason for this is going to be the underlying reason for stuff next chapter. So we want to start talking about that now. Okay. So, did you know that orbitals filled up in order? That there's an order they fill up in? See, he got distracted. We both did. There you go. Okay. And the order they fill up is lowest energy to highest energy. Not energy level, because energy level now means a whole wave. First energy level, one whole wave. Second energy level, two whole waves. Third energy level, three whole waves. So it fills up in order of energy, not energy level, because it fills up 4s before it fills up 3d. So we know it can't be energy level, right? Because if that 4 is the energy level, 4 should fill up after 3 if we go in energy level order. And, but what we didn't mention was that the same orbital is going to have different energies in different atoms because it's going to be repelled differently. Because we talk about the nucleus attracting everything. But every time I put in an electron, it starts repelling those other electrons, which changes their energy a little bit. Okay? So adding electrons can change the energy of the orbital. And usually the change is so small that it's not noticeable. But there are some places where it shows up. Okay, and this is the reason why, and I'd love to give you a great explanation, but they don't have one. But they do know that filled and half-filled orbitals are lower energy. They can explain the half-filled ones, but the filled ones are a little tough. But filled and half-filled orbitals, especially low energy, Hey, and why is it a bad idea to store a bowling ball on the top shelf? Eventually, if you leave it long enough, that bowling ball is going to end up on the ground, right? There's an earthquake, it's shaken, it's on the ground. We let it sit there long enough for the wood to rot. It's going to be on the ground. That bowling ball is going to end up on the ground sometime. So that bowling ball automatically goes from higher energy to lower energy, right? So, and once it gets on the ground, it's going to stay there because it can't fall any further. So the lowest energy something can have makes it stable. So filled and half-filled orbitals, because they're low energy, are more stable. Once you make them, they tend not to change. Or making them is easier. It's easier to put the bowling ball on the ground than it is to put it up on the top shelf. Okay? Does that make sense? Now, it shows up in several places, but the only place I need you to know the exceptions for are in the d orbitals. We're not going to talk about it happening in the p orbitals or the s orbitals. We're only going to talk about it happening in the d's. And the f's, actually it doesn't happen in the p's and the s's. It happens a little bit with the f's, and they're not predictable. They're not reliable. So the d orbitals are going to fill a little bit differently than we've been saying. And it's about filled and half-filled orbitals being easier to make. Okay, so to see if you're breaking the rule, first we're going to follow the rule a couple times and then see what happens when you break it. So write the electron configuration for titanium. Titanium has 22 electrons. So I have to work my way up to 22. Well, I got chlorine behind me right now, so we know it's going to be 1s2, then 2s2, then 2p6, then 3s2. And then that gets me up to 18, and I'm trying to go to 22, right? So next is going to come 3p6, and then after 3p comes 4s2, and titanium I need 2 more, so it's D2, and it's a 3D2, right? So that's what you get. That is the electron configuration of titanium. It follows the rules. So the next element, vanadium, has 1 more electron. What would its electron configuration be? You'd write all that stuff, instead of being 3D2, it would be 3D3, right? It's the next one, right? You add 1 more electron, the D's not full. Yeah, go ahead and turn that off. I got a hammer if it won't go off. Okay. What about chromium with 24 electrons? With 24 electrons, what do you expect? Keep going until you hit 3d4, right? Add 1 more. That's what you expect, but when you look at the light it gives off, it doesn't give off that kind of light. Remember, these S's, P's, D's, and F are really about individual lines of color originally. The sharp lines, the diffuse lines, the fine lines. F stood for fine. They're actually groups of lines. And the lines chromium draws don't match up with the electron configuration. So and the way they know it is because things that have 2 orbitals that are full have pairs of electrons. So where those electrons are paired, there's 2 lines, because one of those is going to have a slightly different energy than the other. So there's 2 lines really close together if there's a pair of electrons. That's how they know there's a pair of electrons, is there's 2 lines really close together. But when you look at chromium, where the 4s line is, it's not paired. Okay? When they look at the light that comes off, they can tell chromium is actually, everything's the same up to 3p6, but then instead of 4s2, it's 4s1. And instead of 3d4, it's 3d5. Remember, the expected one was 4s2, 3d4. So what happens? What happens to the electrons in order to make it switch from here to here? What did you do to make? I took an electron off of the 4s and moved it on to the D. So instead of 4s2, 3d4, it's 4s1, 3d5. Why would it do that? Well, how would you describe D5? How many electrons can D hold? D can hold 10, so D5 is half full. How would you describe S1? It holds 2 electrons, it's only got 1, so it's half full. By moving that 1 electron, I made both orbitals half full. And half full is lower energy. And lower energy is what you make and how it stays. So in our off-bow diagram, this would be 4s and 3d, right? That's 4s2 and 3d4. Okay, that's what we expect. That's not what we get. So what happens is the electron moves out of the 4s orbital and moves into the 3d. We always put the first one in up, right side up. And then once it moves, then that orbital has lower energy. And it stays that way. So let's look at that again. The 4s electron moves to the 3d. And once it's there, it makes that 3d have lower energy. And lower energy fills up first. So I went from S2D4, full and nothing special, to S1D5, half full and half full. Okay? So they're slightly lower in energy, which is the key is that S's and D's start off really close together, so a little difference is enough. So we have an exception at D4 because we can borrow one electron and make it D5, which gives us two half-filled things. Okay with that? Okay, there's another place it happens. Let's look at copper. Copper's number 29. I don't know if you noticed the trend. Titanium with 22 was at D2. Vanadium with D3, at 23 was D3. Chromium at D4, at 24, we expect it to be D4. So at 29, we expect copper to be D9. That would be the electron configuration for 29. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That's what we expect. We expect it to end in 3d9. But when you look at the light, it doesn't end in 3d9. How can we use that same principle that we just did with chromium? How can we apply that to copper? So what did we do with chromium? We took one out of the S's and moved it to the D's. So instead of 4s2 at the end, it's going to be 4s1. And instead of 3d9, it's going to be 3d10. What's the benefit in that? Well, I started off with 4s, one full, and d9, nothing special. Now I ended up with 4s1, half full, and 3d10, full. One full and one half full orbital, both are lower energy. So the places where there's exceptions. These are two places I need you to know. There are other places there's exceptions. They're just not as predictable as these. Don't follow a nice pattern. Okay, we are just predicting them. If I really want to know them, I got to look at the light they give off. So the place where you need to think about the exceptions is at D4 and D9. You should never have an electron configuration that ends in D4. You should never have an electron configuration that ends in D9. Because you can borrow one from S and make that D half full or full. Because there's going to be other places where it's D4. It's going to show up again in the fourth energy level, right? It'll show up again in the fifth energy level. It'll show up again in the sixth energy level. Every time you don't write D4, you move one and make it D5. Same thing with D9. You should never have an electron configuration that ends in D9. You can borrow one and make it D10. So I've told you before, there's never D4. And there's no denying, there's no denying.